Welcome back to Aram Dev Hub. In today's video, we are diving deep into the world of asynchronous programming in Rust. But that's not all. We are going to turbocharge our async functions by integrating caching with the cached library. Hey, rustaceans! I'm thrilled to bring you another exciting tutorial. Today, we are going to explore how to efficiently handle asynchronous operations and improve performance with caching. By the end of this video, you'll have a strong understanding of how to write asynchronous code in Rust and how to make it faster with caching. Let's kick things off by setting up a new Rust project. If you're following along, open your terminal and type the following command. Terminal displays the creation of a new project folder with the standard Rust project structure. With our project set up, let's head over to our cargo.toml file to configure our dependencies. We'll be using Tokio as our async runtime and cached to manage our cache. In the cargo.toml file, add the dependencies. Here, Tokio is our async runtime, and cached is the library that will handle our caching. The Tokio feature set to full gives us access to all necessary utilities for async programming. Great! Our project is ready to go. Now, let's dive into writing some asynchronous Rust code. Before we dive into the code, let's briefly discuss what asynchronous programming is and why it's essential. Asynchronous programming allows us to handle multiple operations concurrently without blocking the main thread. This is particularly useful for I/O-bound tasks, like making network requests or reading files. In Rust, asynchronous programming is facilitated by the async and await keywords. Here's a simple analogy. Imagine you are cooking dinner. While the pasta is boiling, you don't just stand there doing nothing, you prepare the sauce, chop vegetables, or set the table. Similarly, async functions in Rust allow other tasks to proceed while waiting for an operation to complete. With that understanding, let's jump into writing our first asynchronous function in Rust. We're going to create an asynchronous function that simulates fetching data from a remote server. This function will have a delay to mimic network latency. Here, we define a function fetch underscore data that takes an ID as a parameter and returns a string. Notice that this function is marked with async, meaning it's asynchronous. Inside, we simulate a network delay using Tokio, time, sleep, which pauses the function for 2 seconds. The await keyword allows other tasks to proceed during this delay. Close-up of code with highlights on async, await, and sleep function. Now, let's test our function by calling it from the main function. Since Rust's main function can't be async by default, we'll use the hash Tokio main attribute to enable it. Run the code in the terminal and show the output. The terminal shows a 2-second delay after the fetching data for ID 1 message, then displays received data for ID 1. As you can see, the function takes about 2 seconds to execute due to the simulated delay. This demonstrates how async functions allow us to handle tasks that take time without blocking the main thread. So far, our function works, but it's not optimized. If we call fetch underscore data multiple times with the same ID, it will repeatedly fetch the data, even though the result doesn't change. This is where caching comes in. Caching stores the results of expensive operations so that subsequent calls with the same input can return the cached result immediately, rather than recalculating or refetching the data. The cached library in Rust makes it easy to implement caching in your functions. Let's integrate it into our existing code. First, we'll import the cached library and apply the hash cached attribute to our function. With the hash cached macro, our function now automatically caches its return values based on the input parameters. This means if we call fetch underscore data underscore cached with the same ID again, it won't execute the full function. Instead, it will return the result directly from the cache. Close up on the hash cached macro with emphasis on its simplicity and power. Let's see this in action by calling our cached function multiple times. Let's run the code in the terminal. The terminal shows a 2-second delay for the first call, then immediately displays the cached result for the second call. As you can see, the first fetch takes time, but the second one is instantaneous, thanks to caching. This demonstrates the effectiveness of the cached library in improving performance. The cached library also allows for customization, such as setting the cache size or expiration time. Let's modify our function to include a time to live, TTL, of 10 seconds. With this TTL setting, the cache will automatically invalidate entries after 10 seconds. This is useful when you want to ensure that the cached data is reasonably fresh. Let's call our function 3 times, twice in quick succession, and then once more after waiting 10 seconds. Let's run the code in the terminal. The terminal shows a 2-second delay for the first call, an immediate result for the second call, and another 2-second delay for the third call after the cache expires. In this example, the second call is still cached, but the third call happens after the cache expires, so it fetches the data again. This kind of fine-tuned control gives you powerful options for optimizing performance. And that's it for today's deep dive into asynchronous programming and caching in Rust. By combining these techniques, you can write highly efficient, non-blocking code that scales well, even under heavy load. If you found this tutorial helpful, don't forget to hit the like button, share it with your fellow developers, and subscribe to Aram Dev Hub for more in-depth Rust programming content. Thanks for watching, and happy coding!